Can you trace this shape without lifting up your finger and without going over any edge twice? What about this one? Pause here and try. Okay, the first one is impossible. The second one, though, is totally doable. But why? How do we know other than trial and error? That's exactly what Euler figured out in 1736 when he was asked about the bridges in the city of Königsberg. People wanted to know if it was possible to walk across all 7 bridges in their town exactly once without repeating any of them. You can't, by the way, but Euler didn't just say no and walk away, he formally proved it. The people of Königsberg were trying to find something called an Euler path on a graph of the river and bridges. In by graph, I don't mean bar charts or line plots. In graph theory, a graph is just a bunch of dots, called vertices, connected by lines, called edges. An Euler path is a path through a graph that covers every edge exactly once. It's like tracing a drawing with your pencil without lifting it back or going over the same line twice. We'll come back to the bridges later, but let's check out this triangle from the beginning. Without brute forcing it, we can predict whether an Euler path exists by looking at the valences, or degrees, of the vertices, basically how many edges meet at a point. These 2 lines meet at vertex A, so it has degree 2. Vertex B has degree 3, and so on. If a vertex's degree is odd, we call it an odd vertex. If it's even, it's an even vertex. Euler's path theorem says that a graph has an Euler path if there are exactly 0 or 2 vertices of odd degree. In this triangle, only B and C are odd and everything else is even, so there is an Euler path. In the first shape from earlier, there are more than 2 odd vertices, so there's no Euler path at all. But how do we actually find the path? There's no one-size-fits-all shortcut, but one method, called Fleury's algorithm, gives us a step-by-step approach. Let's work through it on this shape with all even vertices. First, if you have vertices of odd degree, you have to start at one of them. We don't, so we can just start wherever. Then, choose any edge leaving your current vertex, provided that deleting that edge will not separate the graph into 2 disconnected parts of uncovered edges. For example, using this edge would make it impossible to return to the triangle part of the graph, essentially severing the graph into 2 separate parts. We'll go this way instead. Then continue until you're done. Awesome, we just found an Euler path. Let's look at our triangle. We have vertices of odd degree, B and C, so we need to start at one of them. We'll start at B. From B, we'll go to D, then to C, then back to B, then to A, and finally, we'll end at D. And this is just one of the many different Euler paths possible on this shape specifically. So that's the algorithm on a couple of toy examples, but Euler paths show up all the time in the real world. Garbage trucks, mail delivery, snow plows, street sweepers, basically everything that needs to cover every street once without wasting time and fuel doubling back. And that's exactly why Euler's bridge problem in Königsberg was such a big deal. What started as a fun challenge about crossing 7 bridges turned into the foundation of management science, the math of planning and optimizing resources. Cities that use this kind of thinking can save millions of dollars by trimming wasted fuel, labor, and time. Oh, and those original Königsberg bridges, every single vertex was of an odd degree, which means that an Euler path was never possible at all. So that's Euler paths, but what about starting and ending at the same place? Those are called Euler circuits, and I'll tackle that soon, so stay tuned.